The word integrating and the word integral, to integrate, integration, it means putting things together, conjoining things, adding things up. And this is where you actually see why integration is called integration. The other part about the primitive functions, the things we call the indefinite integrals previously, we could do it without the idea of integral. We could call them primitive functions. Okay, let's find the primitive functions, the anti-differentials, anti-derivatives, and that's all. So where does this integration idea come from? It turns out, okay, let's suppose we have a function, some kind of graph. First of all, let's suppose this function is positive. We are considering this function on a segment A to B on the x-axis, and let's suppose that f of x is not, at least not negative for all x values from A to B. We are considering a positive function, and we are considering it between x values of A and B. And where the definite integration actually comes from, let's suppose we are interested in the area of this figure. Let's call it curvilinear trapezoid. It's not a real trapezoid because this side is not straight. So we will call it curvilinear trapezoid. And we would like to know the area of this curvilinear trapezoid. There are all kinds of possibilities to estimate this area. For example, I might actually draw a straight line and say, okay, let's pretend it's a real trapezoid. In some parts, my straight line tells me that I have too much, and some parts, it tells me I have not enough for the area. Perhaps it might balance and even out the extra things and the missing things. Then I might think, okay, but perhaps I can simply split it into slices and make many small trapezoids. The thinner the slices, the more accurate my trapezoid is. Although it will never be a real trapezoid, but perhaps if I cut a thin slice like this, it's almost straight. If this slice is very, very thin, then basically we might say it's almost a straight line. The function, the graph of the function, the little piece, the tiny little piece of the graph of the function is almost a straight line. So that would be one possibility, to slice this curvilinear trapezoid into thin slices and consider the sum of areas of very small trapezoids. Actually, that's one of the methods of approximation. That is one of the methods, one of the numerical methods where you can estimate, not calculate precisely and accurately, but estimate the area below the curve, between the curve and the x-axis. Although we are going to, for the sake of simplicity, we are going to look at different slices today. So one of the most accurate methods, slice this area up into very thin slices and say, okay, every slice is basically a trapezoid. If we find the areas of all these trapezoids and add them, then it's almost the same as the area of this. But for our purposes today, it will be easier if we still slice this area below the curve into thin slices, and let's also assume that all these slices have equal width. I know it's not very accurate, it looks strange, but okay, this is x1, x2, x3 and so on, and if we could say that A is x0, then B will be xn, so we have n very thin slices, and the width of each slice will be the same. It's not necessary, but it's the most obvious, the most evident solution, the most, let's say, the most understandable solution, the most understandable method to show you how we can find the area of this curvilinear trapezoid. So let's assume that xi minus xi minus 1, so the next x value minus the previous x value. Let's suppose this is constant, and let's suppose this is, well, for each slicing it's constant. In other words, it's the same for all I values. Actually, I don't want to write constant because we will need it to change. It's constant with respect to I. So I will write for all I values. In other words, this states that the width of each slice is exactly the same. So still we need a method to find the areas of all these slices, and I will do an interesting thing. I will look at the function values at the endpoint of each tiny small segment, and actually I will pretend that all these slices are actually rectangles. So I'll pretend that this is a rectangle, that's the end slice. This is the slice number -1, this is one before, this is the one before, this is the one before, and so on and so on. So we can see that sometimes this rectangle might turn out to be a bit more than the area of below the curve. Sometimes it might be slightly less if the function is, for example, decreasing in some segment. But basically we can pretend that all this curvilinear figure, this curvilinear trapezoid, consists of very, very thin rectangles. Just like this. Perhaps you have seen paper art where some artists take a thick pile of paper and then cut sculptures of that. So this is something like this. If you imagine that the slice is very, very thin, like a sheet of paper, then obviously if you take a whole bunch of those pages, you can take a knife and sculpt. So this is something that might happen here. Of course, we can say this is highly inaccurate at this moment. Well, not highly, but rather inaccurate. But on the other hand, this is the function value at the point x1. This is the function value at the point xn. This would be the function value at the point f of x n minus 1. So at the point x n minus 1. And so on and so on. So we can basically write the area of each of these rectangular slices, which are not really the slices of this object, this figure, but, well, close enough. Close enough. So the area of each tiny rectangle, or not so tiny, but at least very, very thin, the area of each rectangle will be f at the point xi, so the right-hand endpoint, times the width of the rectangle, which is delta x. This thing. So this would be the area of the rectangle number I, the ith rectangle, and if I add them all together, sum I from 1 to n, we have n rectangles, and I'm looking at the right endpoint of each interval on the x-axis, then this sum, we might think, is approximately the area below the curve between A and B. The thing is, if we are not satisfied with the accuracy of this result, we can make those slices thinner. If I make those slices thinner, what happens is like this and like this. You see the extra parts become smaller. If I make these slices thinner, see those extra parts, the inaccuracy, the error becomes smaller, and the thinner those slices become, the less this inaccuracy, less this error becomes. So I might say, all right, perhaps we could take the limit when delta x tends to 0, which seems a natural thing for a mathematician to think. So we call this the integral sum of n segments. This is the upper integral sum. We could take the lower integral sum if we consider the endpoints on the right. For example, we could also say, okay, let's not take the right-hand endpoints of each segment. Let's take the left-hand endpoints of each segment. You see, this is now, you can see this is now it's still inaccurate, but now there are missing parts. There are no extra parts. There are missing parts. So it's not enough. If the first sum seems, at least in this case, it seems to be too much, then this sum on the from the other endpoints of these segments seems, you can see, not enough. Not enough. But the interesting thing is, as we make the delta x become smaller and smaller and smaller, the difference, of course, becomes less and less and less. And in the end, when we take the limit, they will probably, well, not probably, but they will tend to the same value. And therefore, I'm only considering one of these sums. Normally, in the academic course of mathematics, we would prove that both these sums actually tend to the same value, that the limit is the same exactly, no matter what method we choose. Even if we choose the trapezoid method, even if we choose to make little trapezoids instead of rectangles, it would still be exactly the same limit if, of course, delta x becomes very small. So I would say, okay, let's take the limit of the sum I1 to n f of xi delta x. Delta x tends to 0, which means simultaneously n, the number of those slices, tends to infinity. Choose whichever you want, they mean the same thing. In this case, they mean exactly the same thing. I'm just writing both, just to let you know that these both statements are true at this point. And we would say, okay, so let's call this the area below the curve. So let's define this as the area below the curve. The definition is the area below the curve. And this limit has another kind of notation. The Greek sigma becomes s, or rather s, like this. Now, instead of I is 1 and then we write the boundaries from A to B, function of it, and delta x becomes dx. So we see where this notation comes from, and we see where the integral notation comes from, and actually this was the first, this came first. The sign of integral that we use for primitive functions historically came later, afterwards, because the idea of integration comes from this problem, from this idea. And then it turns out it can be proved that this kind of integral is closely linked to the primitive function of f. And it can be shown. So for now, the general idea is this is where this definite integral comes from. This is the definition of a definite integral. But mind you, we are still considering only a positive function at this moment, as the area, because the function value is positive, so the sum of all these rectangles, the areas of the rectangles, positive rectangles, positive area values. If I try to multiply this by delta x for a negative function, this product would be negative. We don't know anything about negative areas. Maybe in a parallel universe, not in this one. So for now, we still needed the fact, or needed to assume that this function was positive all the time for all the x values in this segment, a and b. So that's one part, the definition of the area below the curve. In other words, between the curve and the x-axis, between the boundaries, so these are called the boundaries of integration, a and b, the lower boundary, the upper boundary, or you may say bounds, the lower bound, the upper bound. This is the area. Now, okay, how do we calculate this area? How do we prove that this indeed has something to do with anti-differentiation, with primitive functions? If we imagine the area function, I'm not going to give you the total, accurate, precise proof. I'm simply going to, well, give you an idea why the primitive function and the definite integral are connected actually. If you imagine the area a of x as a function, and this function would be the area, from a to some value x. In other words, this function would be positive, it would be increasing because the further on we go here, so ax, from a to x, this would be the area a of x for any value of x between a and b. This is the area function. Now, if we want to derive the area function, remember the derivative of the area function would be, okay, I will write lim delta a over delta x when delta x tends to 0. That's the definition of derivative, right? So what is delta a for some delta x? If I look delta a that corresponds to this delta x, what is that? It is this. It is this. It is this. So the area, delta A is this area of one slice. If I divide it by delta x, what do I get? 1. I get the function value. Because the area of this rectangle, which is delta A, it's the area of the rectangle basically. This delta A. The width of that rectangle is delta x. If I divide the area of that rectangle by delta x, by the width, I get the height, the function value.
We can see from there also.
No, we can't see it there.
To find the
No, we can't. Well, we can use it, yes, but simply because I used this notation. The notation alone does not mean it has something to do with primitive functions and anti-differentiation. It's simply notation that happens to be similar to the notation we used before for primitive functions. That's the thing. This actually proves that the notation is chosen deliberately. This actually proves that the notation is chosen deliberately. Because for any specific x value, if you divide the area of a rectangle by its width, you get the height. The height of this rectangle is the function value at that point. For this x value, for example, for this particular x value. So, if the derivative of the function value is the function f of x, then obviously the antiderivative or the primitive function of f of x is this function. So actually I show that if I derive the area, I get the function f of x. In other words, if I find the antiderivative, the primitive function of f of x, I get something connected to the area. And that's why we can actually say that yes, this does have something to do with the primitive function. And now, Newton in England and Leibniz in Germany discovered this connection at the same time. So in those times, there were no emails. So they sort of competed in mathematics. They were the two people who actually created the basics of calculus altogether, the idea of infinitely small quantities, infinitely large quantities, rates of change and limits and things like that. They worked, they worked, you might say, on parallel courses, and they corresponded, and they both discovered the formulas at approximately the same time. But because there's no email and you can't say, well, I sent this email at exactly that moment, so I was the first, I discovered it first. No way to check timestamps on Skype or something. So the formula is named after both of them, the Newton-Leibniz formula, which actually links. So Newton-Leibniz formula. Newton-Leibniz formula. It's also called the fundamental theorem of calculus. which states that this area below the curve of a positive function between the x values a and b equals the value of the primitive function at b minus the value of the primitive function at a. This. No more, no less. And this is called the fundamental theorem of calculus, or expressed by Newton-Leibniz formula. And this is actually the connection between antiderivatives, integration as we know so far, meaning finding primitive function, finding the function whose derivative is known, and finding the area, the integration in the geometric sense. And it's the geometrical idea of integration that actually gives us the notation with the integral sign, as you saw. So Newton-Leibniz formula can actually be used to find the area below a curve. For example, if you need to find the area below, let's take something very simple, an example. Let's suppose we need to take the area below the curve, let's say y equals x squared from x equals 0 to x equals, let's say, 3. So if we want to find this area, for example, now I know that I can do this if I write the integral from 0 to 3 x squared dx. So now I find the primitive function, but we don't use the integration, the constants of integration, because the constant of integration would cancel out anyway if we subtracted both these values, right? It's just an added constant. So the primitive function of x squared is x cubed over 3. Then we put this expression, the primitive function, into square brackets. We still keep the boundaries of integration from 0 to 3, and now we simply put them in. We always put the upper boundary in first into the primitive function. So I would say 3 cubed over 3 minus 0 cubed over 3, which is 9. I could say square units, because I don't have any specific scale. Nobody has told me that the unit has to be 1 centimeter or 1 meter or 1 inch or something else. So this is how we find these areas. We integrate the function, actually integrate in the old sense, meaning find the primitive function. Then we put in the upper boundary, the lower boundary, subtract the values, and what we have is the area. So this is basically it. Pretty simple, I would say. You don't have to know this in finer detail. I showed it to you, well, for several reasons. And one of these reasons is because you need to know why we can use integrals for so many purposes, for actual calculations in physics, engineering, economics, everywhere. Okay. Now I'm erasing this. We have some rules, as you see on your handout papers. As we see on your handout papers, we have some rules, some laws or properties of the definite integral. It's called definite integral because it has definite values. The indefinite integral has no specific values, it's simply a set of functions. So it's indefinite, we don't even know which function we are using. The definite integral is basically the value of a definite integral is always a number. It can't be anything else because we put values in there. So we might use integration as in finding the primitive function, but then we put in the boundary values, so the final answer will always be a number. Okay. So now, we move away from the idea of this function always being positive, because if we define a definite integral like this, we could actually use any function there, forget about the areas, and say, okay, the definite integral of some negative function, put in the values, it will be some negative value. Okay, we don't have to think about the areas all the time. This is the area is where this idea comes from, But of course we can apply this method, we can apply this formula to all functions, positive, negative, whatever values they have. Only if the function is negative, then we cannot talk about actual areas anymore. But the formula works, the definite integral exists. We can calculate it, we can find values. And so the properties, the integral from a to a, well, obviously, if both the boundaries are equal, if they are the same, then the value of the integral will be 0. That's the first property. Second property, the integral of a constant function is c times b minus a. Yes, because the integral of a constant, the primitive function of a constant c is cx. And then you put c times b minus c times a. Or, if you think geometrically, if c is a constant, the graph is a horizontal line, and the area below a horizontal line is a rectangle. Length b minus a, height c, and there you go. The third formula, if you switch the boundaries of integration, and it is possible to write the greater value down and the lesser value up there. So if you exchange the boundaries of integration, then obviously the integral value will change the sign. So that's the next property, the third one. Number 4, if you multiply a function by a constant, then the definite integral is again the constant times the old definite integral, just the same as with indefinite integrals, because that's how indefinite integrals work. Then, of course, if I put c here, a constant factor here, then we will have a constant factor in front of both these numbers, so it will be the same. So you can take a constant factor out of the integral or into the integral as necessary, just like you do with indefinite integrals. Number 5, you can integrate the function from a to b, that will be one area, and then from b to c. So you can actually split this area into 2 parts and integrate like this. Or if you prefer a proof by Newton-Leibniz formula, of course from a to b plus from b to c, you will see that the b value will disappear and you will get f of c minus f of a. Again, easy to prove. We can combine 2 integrals in following intervals, no problem at all. And finally, if you have a sum or difference of 2 functions, then the definite integral can be written as the sum or difference of the integrals of those 2 functions separately. Again, it depends, or it is because of the properties of indefinite integrals. Because we have shown, or rather Newton and Leibniz have shown that the definite integral has a connection with primitive functions. So a lot depends on the properties of indefinite integrals. And finally, if the function and the integral is negative, we can still find the area between the graph of a negative function and the x-axis. If we integrate, of course, a negative value times dx, of course this integral will be negative. But then we say, okay, we need the area is always positive, so we'll take the absolute value, the modulus of this. Or we can simply exchange the signs, exchange the boundaries. So if we have a negative function, we can still find the area. We simply remember that the area is always positive, so we can change the sign of this number, which will be negative. We can put the absolute value on this integral. So if this is a, this is b, and this is the function f of x, then the area of this will be absolute value of integral from a to b of the function f dx. The absolute value. Or you could simply write minus in front to indicate the sign change instead of the absolute value. Or you can simply exchange the boundaries of integration, which also changes the sign. You just have to remember that although originally we started with positive functions, it is possible to deal with negative functions with a little bit of adjustment. Yes, question?
Yeah, if we will not change the boundaries, if we have anyway the negative signs, we will not change.
So you will have the integral which is negative, but you cannot say that this is the area because an area cannot be negative. So we understand it's negative because the graph is below the x-axis, but, well, to address the geometrical problem correctly, we have to make the area positive, so we simply take the absolute value. So this is simply a way of dealing with these areas. Alright, so later, now actually I want to do it now so that we can focus on exercises afterwards. Area between two curves. If we have two graphs, two functions, if we have two graphs, two functions, for example, okay, like this, the function y equals f of x, and the function y equals g of x, and we need to find the area, for example, between these two curves. So first of all, if these both functions were positive, it would be easy. Then I would have a positive function, I take the boundaries, the intersection points, although sometimes it's possible, sometimes you will be asked to find the area, ignoring the intersection points but somewhere else. So to do this, obviously, I have to find the area below the upper curve. So the first area would be area 1. From A to B below the curve f of x. Then I have to take the area below the bottom curve and subtract it. Because basically the area below the upper curve is all this. From that we need to subtract the unnecessary part, which is the area below the other curve. So A2. This is the upper and this is the lower. A2, the second area is from A to B below the bottom curve, the lower curve, and then you have to subtract A1 minus A2. But remember, if you have a difference of two integrals in the same segment, you can simply subtract the two functions in one integral. Using the properties of integrals, you can write from A to B f function, the upper function, minus the lower function. If you get confused, if you start subtracting the top function from the bottom function, then of course you will have a negative area, which is a problem, but then you will notice that probably you made a mistake. You have to look carefully at which graph is on top and which graph is on the bottom. Now, what happens if we have functions that can be positive or negative? This works fine. This works just fine if you have to find the area between two curves which are both positive. What happens if one of them is positive, the other one is negative?
Do the same.
We do the same. Why?
Because
What? Because what?
Because
So we could, of course, look at the point where the functions become negative and split it into separate parts and see where you have to add, where you have to subtract, and so on. But we can imagine it like this. Let's add some constant to both of these functions. This means that both graphs travel up c units. And let's take the constant such that both graphs are actually positive. So let's push them up enough for them both to be positive. But we add the same constant. Now, of course, if we only move both of them in a similar manner, the area between these two curves is the same. So, of course, if I subtract now f of x plus c minus g of x plus c, the constant c will cancel out. And we still have exactly the same formula. So, for today,
So there must be A1 minus A2?
it's real.
No, in the rectangle that you made, the red rectangle.
But
And you
how
have,
is it?
yeah,
I'm reading the formula.
A1 minus, oh sorry, yes, A1 minus A2, of course.
Yeah, it's
You are right. Of course, A1 minus A2.
Trish.
So we had first the idea of integration in general, the approach, the area approach to this process. Then we saw that it indeed does have a connection with primitive functions. So this is a very important formula, the Newton-Leibniz formula.
This one.
This is the formula for the area between two curves. The area between two curves, which works no matter whether the functions f and g are positive, negative, changing signs, or whatever. Of course, there might be this situation where one function is on top in one part and then the other function is on top in the other part. Then you have to split the whole integral into two parts. Because here you will have f of x minus g of x, and here you will have g of x minus f of x, of course. You have to make sure this difference is always positive. So that otherwise it will happen that some part of the area will be normal with a positive sign. If you don't notice that at some point they switch places and this area becomes sort of negative and you integrate it all in one piece, like this, then some parts of positive negative values will cancel out. So you always have to be careful and subtract the lower function from the upper function. And notice all the points where they might switch places. But that will be probably later. I'm not sure if we have time enough to do it today. I simply wanted to do all the theory today and then see what happens with the exercises.
sorry. But the lower function and the upper function.
Which?
Yeah.
When you need to know, first of all, you will have to sketch. You will have to do the graphs. Not necessarily extremely accurate graphs, but obviously the intersection points are important. And it's important in each segment to know which function is on top and which is on the bottom. So yes, because here they switch places. If this part, if you integrate, it's positive, then here, if you don't change the integral, it will be negative, because from the from the smaller value, we'll be subtracting the greater value. So but we will reach those exercises, we will reach them in time. So now, the first exercise actually has nothing to do with integration, and everything to do with the idea of what this definite integral actually is. Use graphical evidence to find the integral. Yes, you can from 1 to 2 to minus x dx. A very simple one. Of course, you can find it by integration, but it's much easier to figure out this problem geometrically. 2 minus x, the graph is a straight line, x is 2, function is 0, if x is 0, the function is 2. This is the graph. We are interested in the area between this graph and x-axis, where x is between minus 1 and 2. So, alright, minus 1, 2 here. So we are interested in this area. We don't really need an integral.
4.5.
We don't really need an integral for triangles, for areas of triangles. So it would be 4.5 because we have a triangle with base 3 and height 3. This is also 3. So yes, 9/2, 4.5. We don't need to integrate. Of course you can integrate, so square units. You can integrate to do this, and many people do, but I know many people actually choose to do this when they have some part of a problem in a simple geometric form. So for this we didn't need to integrate. The second one, from 1 to 3, 1 plus 4x dx. 1 plus 4x, so 1, and the gradient is 4, so it's pretty steep. So it's pretty steep, comparatively steep function, okay? From 1, let's suppose, from 1 to 3, I don't need the actual scale. I only need to understand how the graph is located, how this straight line actually is, where it is situated in the plane, and to realize which area I actually need. This is not a curvilinear trapezoid, that's a real trapezoid. So the basis, we need to find the basis. If x is 1, so this is y equals 1 plus 4x. If x is 1, then the function value is 5. So the smaller base, shorter base is 5. If x is 3, then y value is 13. So the longer base is 13. The height of the trapezoid is 2. So the area of the trapezoid is 5 plus 13 divided by 2 times the height, which is 2. So it's 18 square units. And again, yes, you could integrate this. X plus 2x squared, and then put in the boundaries, no problem. But sometimes it's enough to do this. X absolute value, x modulus. Minus 1, x absolute value dx. To be honest, we don't know how to integrate absolute value of anything. We have to split it up into 2 parts and so on and so on. But if we remember geometrically, if we remember what it looks like, remember the graph of the simple absolute value has a V shape, just like this. Minus 1, 1. We need this area, which is 1. 1/2 plus 1/2. So again, using geometrical considerations, easier to solve than by using integration actually. And finally, oh my favorite one, minus 2 square root 4 minus x squared dx. Oh, yes, if you want to integrate this, you need a substitution. We need the substitution x equals 2 sine t. A new variable t, which makes x a double sine. But on the other hand, y equals square root of 4 minus x squared. What is that? If we square both sides, y squared is 4 minus x squared plus y squared is 4. Anything familiar?
Circle.
It's a half circle. Obviously, from this we can see that because this is the main root, y cannot have negative values. Y is always positive or 0. So this is a half circle. Y equals square root of 4 minus x squared, but it's a half circle. Minus 2, 2, 2. And we are interested in this area, which is half of a circle. Which is half of a circle. So definite integrals are often easier to find than indefinite integrals. And there are many numerical methods of approximation to find the approximate values to, well, with whatever accuracy we like. With whatever accuracy we like. But in this case, so it's half of a circle. So it's 1/2 pi r squared, and r is 2, so it's 2 squared, so it's 2 pi square units. And that's it. But if you wanted to integrate this by using methods of integration, then it would be very difficult. So then we would say, okay, let x be 2 sine t, then t is, oh no, arc sine of x half. That's unpleasant, right? It's not nice.
use integral.
But yes, you can actually integrate using this substitution. It is possible to integrate that using this substitution. So those of you who have
By the way,
curiosity can try. Yes.
how you know it's semicircle before you, like when you see this?
Because when we have the radical sign, the square root sign, it always means the main square root, which is always positive or perhaps zero.
Yeah.
Because if I mean the negative root, then it would be minus in front.
Why is not circle?
Because y is only positive. Y has only positive values for this. It would be full circle. If it would be full circle, then I couldn't find that integral. I would have to write two integrals of something. Okay, so this was the easy part. No integration at all. Number 2, find the area between the x-axis and things, lines. So now you can try to do exercise 2 because it's simple integration. I never put complicated integrals, complicated methods of integration in the definite integral. So the definite integral should be easy enough for all of you. These are simple functions, easy to integrate. In exercise 2, A, B, C, and D, you are given the boundaries of integration. In E, you are not given the boundaries, you have to find them.
Oh.
Okay.
Because what happens, this is a parabola, the ends of the parabola goes down, so obviously this parabola intersects the x-axis at 2 points. So what you have to find is the area between the two intersection points.
Oh, okay.
Because below this graph, between this graph and the x-axis, it's this part. Only you have to find the boundaries of integration. And yes, one of them will be positive and the other one will be negative. Okay, try it. And in 3, if you have to find the area bounded by not bounded by, but if you have to find the area between a curve and the y-axis,
Minus 2 and 3.
you do exactly what?
Minus 2 and 3.
Oh, you already did it. Okay. Fine, no problem. Absolutely no problem. You might notice that whenever we deal with quadratic functions, we get areas in terms of 1/3, 2/3 or something. It's simply because the integral of x squared, the primitive function, is x cubed over 3. So if the boundary values are not divisible by 3, you will get some thirds there.
This was minus 3 and 2, but the boundary.
For E,
Yeah.
no, minus 2 and 3. Minus 2 plus 3.
How to solve the integral?
Which one?
Integral from A to infinity.
We will.
I forgot how to do it.
So first of all, from A to infinity, first of all you integrate. And then you put infinity as one boundary and see what happens.
Okay. Maybe
Because it depends on the function. Sometimes we say, oh, this integral diverges, it's infinity, you cannot, the value would be infinity. But sometimes when you put infinity instead of x, you get the infinity in the denominator, which means division by infinity, it's 0. It will have a value, and so you will be able to find the second.
so either infinity or 0. Almost.
Yes,
Okay.
yes. And so if you have to find the area between the graph and the y-axis, you have to change everything into y. So the boundaries have to be between two y values, the function has to be expressed x in terms of y, and the integral will be in terms of dy. Then exercise 4 is simply evaluate the definite integrals. They may be negative. They may be negative. So in exercise 4, on the second page, you don't have to think of this in terms of area. These integrals are simply for integration. So you find the primitive function, you plug in the boundary values, and you find the answer as a number. That's all. You don't have to think about positive, negative, about areas at all. Because we integrate not only when we need areas, when we need other things as well. So, okay. I believe I did send you, I think, the answers, this file and the answers. Yes, I did.
Yep.
Yes, I did. So you should have the answers, and if you have any questions, please ask. Okay, so you integrated, now you got to apply the boundaries 1 to 0, so it's 1 over 1 0, 4. That's all. That's how you do it. Okay, all questions? No, because this was just an exercise to show you that the integral gives us the area, and so sometimes if we see the area, we can find the integral without it's not always. Sometimes it's easy. For these, it's not easy. For these, it's better to integrate. But for triangles, rectangles, if they're only straight lines, it's easier geometrically.
And you said the answers, right?
I did?
And plus filter and it from
You
0.
send separate?
In the same mail. Let me check. Let me check. Let me close. Two attachments, yes I did. Yes I did. Because I rearranged the exercises, I had to cut those answers from my old file. It will probably look nicer at home on a larger screen. I think larger screen will be better. Home, because then you can look at them properly, easier to see. Yes, you have all the answers. Yes, of course, we will continue with some selected exercises next time. We still have time.